small one, but now I'm scared. Looking at you, trying to see your stalling. Ooh, one hesitant step ahead. You're another small one, but now you're scared. Looking at you, trying to see where you're crawling out. Emergency, oh.
Good morning, everybody. Good morning. Good morning, everybody.
Good morning.
That's better. Hi, I'm Konstantin. You might or might not know me, as he said, for Sinatra, Reg, Travis CI, whatever. And today I'm going to talk about death to cookies. If there is one thing you take away from this talk, it's that cookies are really a half-baked solution for authentication. That was a joke. God. Okay, so throughout the ages, people have come up with all different kinds of cookies. But those are not the cookies I'm going to talk about today. And I'm going to talk about how evil hackers abuse these cookies to infiltrate your systems. It's story time. Our main characters, Alice and Bob. Alice and Bob have a long-distance relationship. It's really complicated for them. Who in here is in a long-distance relationship? Okay, gotta ask you about that later. Anyways, besides their passion for each other, they have a passion for cookies. And I'm talking about real cookies, not the one you have in your computer. So Bob wants to open a cookie store, but he doesn't have any recipes. Alice has an amazing collection of recipes that she wants to transfer to Bob in real time. They are looking for some way to use the web for this, and are looking and not finding a solution. We, the web developers here at DevCon, get wind of that and discover a niche market. So we develop our own web application called Recipetastic. We hire a designer, get some VC funding, and the end result looks something like this. As you see, we use modern technologies like Bootstrap and HTML. How does this work? This is Recipetastic, trademark pending. So Alice enters the recipes into Recipetastic, and Bob reads them from Recipetastic. Pretty easy. Now all we need to figure out is the pricing, and we basically have a money cow. Except, enter our two nemesis. Nemesis. Okay. The first one is Eve. Eve wants to get a hold of the recipes, and we need to prevent that. Eve wants to steal them and bake those delicious cookies herself. The other one, even worse, is Mallet. Mallet wants to modify the recipes and add poison so that everyone that eats Bob's cookies will die. How do we solve that? Well, it's pretty easy. Smart web developers that we are, we add a login. Up there, problem solved. And since we know technology, we choose the best tool for the job, cookies. Quick reminder of how that works. So Bob fills out that form up there to log in. That will trigger an HTTP request that looks something like this. It includes email is bob@builder.com, the password, stop motion with a 0 and a space. It's really secure. And our web application returns the HTTP response This is what the browser and the web server are talking. I guess a lot of you have seen something like this. Who has seen HTTP? Cool, yeah. So the browser responds with the headers. This is the part up here. Down here is the HTML that sets user to Bob. And then whenever Bob's browser sends a new request, it will include a header, cookie header that says user equals Bob. So for every request, our server knows this is Bob. Problem solved, right? Okay, let's enter the first attack. So let's assume Eve goes to the website and checks her cookies afterwards and sees that there is a cookie called user and it's set to Eve. So Eve can just start guessing. And this is not correct. There needs like a cookie colon here, but that would be too long. Eve could just set the cookie user to Bob. And now our website would believe it's Bob. Whereas Mallet could set the cookie to Alice and modify the recipes. That was a pretty easy attack. So how do we solve this? Well, how about we set a second cookie to where we store the password? That way, Eve would also have to guess the password. Now every time we get a request, it will include the password there. And congrats, you just implemented basic auth on top of cookies. Well, you might say, hey, I don't want to transmit the password in plain text, which you actually also do on the login, but whatever. So you could technically store a token. It's basically equivalent. It's like having a second password that's generated. And yes, problem solved, we're happy. Enter the first attack, cross-site scripting. I assume a lot of people might have heard about, or no. Have you heard about cross-site scripting? Yes, nodding, good. So it basically works like this. If there's a form field or something, they can just add some HTML tags that will be added to the website. And this is some JavaScript from evilhackstore.com, a very trustworthy page. And in that JavaScript, you can, for instance, read cookies with document.cookies, and then you can just send them somewhere. And well, this is actually easily solved. When you set a cookie, and the web framework will do for you for sessions, you can add an HTTP only, which causes it to not be available to JavaScript. Yay. But if you can actually execute JavaScript in the website, you can also just read and write the recipes instead of reading the cookie. And we're set again. The solution, of course, is to sanitize all user input, which I hope you're all doing. And there's something called the content security policy where you can say a header that says like, do not execute JavaScript that's inline. Do not execute JavaScript that comes from a foreign domain, etc., etc. I really recommend you look into that. Next attack, cross-site request forgery. Who has heard of that? Nodding, nodding. Fewer people, but some, yes. So how this works is, people like Eve or Mallet create another website that looks really interesting that you go to, and it looks harmless. But on their website, Mallet could include an image tag where it just says, go to Recipetastic, like include as Recipetastic / create content, mix flour and poison. And that would just trigger a GET request, and we have deadly cookies. So HTTP has a lot of, for protecting this, HTTP gives us a lot of methods. Anyways, we can use post, which we use by just in the form on our website saying method equals post, and then an image tag will not trigger a post request, problem solved. No, actually, now Mallet could include some HTML that's invisible, display none, because she has amazing CSS skills. And that has a form just like ours that says method equals post, and it's in a hidden iframe, and it again has mix flour and poison. And then she just uses some JavaScript, say like onload, submit this form, and then we get a post request, and again deadly cookies. So what do we do? The first thing we can do is there is a header called referrer. It includes the web address a request is coming from. And yes, referrer is supposed to be spelled with a double R, but it's not an HTTP because they did a typo when implementing it. If you would use Sinatra in Ruby, you could check this something like that you say like, the request referrer should start with our base URL, otherwise we're just gonna do access denied, problem solved. No, unfortunately not. Because if the request is coming from FTP or HTTPS, it will not include the referrer header, because it might include secret information that the browser doesn't want to leak. Also, if the user has an outdated Flash plugin, referrer can be overwritten to anything, so we basically can't trust it. Well, the people that develop HTTP also know about this, so they came up with a second header to avoid the issue of leaking confidential information that might be in the URL. And it's called origin, and it just includes the scheme, the domain, and actually the port if it's a non-standard port. This actually would simplify our code, because we only have to directly compare the origin header to our base URL. And then we also, this back here is to check like get requests should come through, otherwise no one can come to our main page and log in, because in order to go there, they would need to come from our page. So kind of chicken egg situation. But problem solved. Or is it? No. It's not supported by older browsers. And again, if your Flash plugin can fake the referrer, it can also fake origin, right? Makes this a set cookie again. So the actual solution is what most web frameworks do, or the solution to this specific attack, is adding a CSRF token to the form that is a randomly generated token, and having that token also in a cookie. And now when we get a post request, we check that the CSRF token, which is randomly generated back here, equals the CSRF token field in the form. Otherwise, we give them an access denied again. Perfect. This is what, for instance, Rails does to protect you. This is also Sinatra has some variant of this. Django has, etc., etc. I'm gonna come back to that, but let's look at same origin. Have you heard of the same origin policy? No nodding. Are you still listening? Cool. Cheating same origin. So same origin is this thing where you can only load JSON from the same origin being schema plus domain plus port. So if you have a JSON endpoint that's authenticated by cookie, which a lot of them are, like if you just add JSON endpoints to your, say, Django or Rails application and people log in and you track that via session, then you're relying on same origin to work. So say we have an internal JSON API that returns the recipe, the steps as an array. It says smash X violently. And so if we wouldn't have same origin in the web browsers, then an attacker could just load that in their awesomewebsite.com, given that Bob goes there and Bob is actually logged in. But Ajax can only be loaded from the same origin, or via cores, in which case you're explicitly exposing it. So that should not be a problem. The attacker should not be able to load the JSON, right? What the attacker could do, though, is include it in a script tag and load it as JavaScript, because JSON is a subset of JavaScript. Well, that still seems harmless, because that's like a top-level array that's executed, but you can't reach it. Well, so JavaScript actually allows you to override the array constructor. So if you override the array constructor before loading the JavaScript, you can insert your own function, what to do. In this case, up here it just says, it's pretty small, but just trust me. I also have the slides online, and I have a project on GitHub down there that demos the attack. But that only works in older browsers, because newer browsers explicitly have a fix against this. So in this case, it just writes them to the website you're visiting. But it could also just send that to Eve per email or something, and then she has the recipe. So we're set cookie. So what do you do? Well, one solution is to never serve JSON that has an array at top level. Or the solution to all of these attacks is actually don't use cookies for authentication. But that's an aside. So we're happy again, are we? Right? So a few months back, an attack became known. So every browser constantly improved the same origin policy for that JavaScript implementation. However, any of you remember that Internet Explorer also supported VBScript, VB being Visual Basic? Turns out they forgot to properly implement it there. There were edge cases where you could just ignore same origin for VBScript. This has been fixed in the latest security release of Internet Explorer 8 and so on, but I'm not sure if people that use Internet Explorer actually updated to that security release. So what can we do about that? Fortunately, there's a really, really easy solution to this. Just block Internet Explorer before version 9. No, so what you actually do is you also require the CSRF token for JSON requests, even if it's a GET request, and then they don't go through. And we're happy. Happy as can be. Our application is secure. Are we doing good so far? What do you think? Anyone thinks we're doing good so far? Let's take a more distant look over the overall picture. Can we trust the cookie? So for one, cookies are based on domains, right? That's the whole scoping for, and there's also a text based on that I'm not going into. Like cookie tossing, there's a good blog post on the GitHub blog because they were affected by this. But for instance, you can fake domains by DNS cache poisoning. Depending on the situation you're in, this is either really hard or really easy. But let's assume we can trust DNS. Can we trust the browser? Can we trust our browser to implement that correctly? Can we trust the browser to not do anything malicious? Well, I guess in general, yes. Because I guess that the people behind that, even behind Internet Explorer and so on, actually somewhat know what they're doing. But going further, can we trust browser plugins? Basically, modern browser plugins are just JavaScript that you load into every page. That's just the definition of cross-site scripting, right? And people just willingly install them, myself included. There's this plugin I had installed for a while. It's Cloud to But Plus. It would, in every website, replace the word cloud with but and the word the cloud with my but. So get ready for the cloud becomes get ready for my but. I deinstalled it when a redirect to cloud, CloudFront, got me to a porn website while I was demoing some code to someone. Anyways, I never checked the code of this plugin. I never checked the author. There's no signature, no trust in there at all. That plugin could, besides having replaced cloud with but, also send all my secrets somewhere else. All my delicious cookie recipes, for instance. So you can't really trust that either, can you? So one thing you can do, and most web frameworks do, is you sign your cookie. You sign your cookie so with the secret that only the web server knows, so you know that the value of the cookie is something you generated, you or our application generated. Furthermore, you can encrypt the cookie so that even malware cannot actually look at what's in the cookie. Well, it turns out there's a certain type of attack that actually doesn't care if you encrypt the cookie, doesn't care if you sign the cookie. It's eavesdropping, because if you get hold of a valid cookie from someone else, it doesn't matter if you understand it, you can just use it and you're that person. There even was a nice Firefox plugin, because you say like, oh, I need a man in the middle, I need to somehow get that cookie. It's actually, in general, it's hard, assuming that you're not an ISP, assuming that you don't have access to the cables. But turns out, if there's an open Wi-Fi that's not encrypted, you can just read all the traffic in the Wi-Fi. And there even is a Firefox plugin. It's called Firesheep. It just monitors the Wi-Fi traffic and then knows different websites and just lists the accounts it captures on the side. And you see there's a Google account, a Facebook account, a Twitter account, a Flickr account from random people on the Wi-Fi. I actually tried this out when it came out. It works perfectly. And you just click on that name and you're logged in as that person. And so Firesheep does not support Recipetastic right now, but I guess it wouldn't be hard to edit. That's really bad. So how do we solve that? How did Facebook solve this? The magic SSL. With SSL, everything is encrypted, so the attacker cannot parse a cookie from the stream. Or can they? Recently, there were 3 SSL-based attacks that came out. The first one was actually suspected to be there for a very long time, but no one implemented it, so wasn't sure. And the thing you have to know about these attacks, really important thing about these attacks, is I think they come up with the name first, like the acronym, like the short name, and then they think about what it could stand for. So the first attack is called Beast. Browser exploit against SSL TLS. Beast allows you to decrypt the TLS stream via injected JavaScript. Depending on what you view a long time, like it's not super easy because it actually takes a shit ton of requests that you need to trigger, say by luring someone to go to your website, and you need to be able to capture the encrypted stream, and it takes about, on a normal machine, if you run it like against my laptop or whatever, it would probably take about half an hour to crack it. But still, if someone seriously wants to crack it, like, you need to have someone for half an hour on your website, but if your website is like, how long can you watch this 9 cats? Someone stays there for longer than half an hour, like bingo. All that delicious cookie recipes are mine. So the thing is, this is actually fixed in TLS 1.1. And TLS 1.1 came out in 2006, so why am I even talking about this? The problem is, or TLS 1.1 came out explicitly also because they knew there's probably a vulnerability here that people can abuse. But no one demonstrated, like implemented the attack until the end of 2011. So no one actually switched to TLS 1.1 until then. How can you solve this? Well, for one, you can force a recent browser, but it's actually easier than that because, and modern web servers do that, you can just simply not accept TLS 1.0 requests. And so this problem was solved. And SSL was secure again, and everyone was partying. Until, well, the next attack. It was a big thing last year, you might have heard about it. It's called crime. Compression ratio info leak made easy. It sounds really professional until the made easy part, but it's really not that hard. So I would not know how to implement Beast, but I could probably implement crime. So it's really made easy because I'm not really a smart guy, I just pretend to be. So encrypting all your traffic really multiplies it. So your traffic increases dramatically with using TLS SSL. To fight that, to make it feasible to use, SSL has built-in compression. And this built-in compression is, like most compression, dictionary-based. So it tries to find the longest string that appears multiple times and replace it with a really short string. And before that, say, like, if you see that short string, please replace it with this long version. That's like the basic idea, and then you use like the Huffman algorithm or something to find a good ratio. Because if you take it too long, then it's not often enough in there, and so on. Seems legit, right? I want that, because it makes my website fast again. Well, so it turns out that the attacker can abuse that to find out the value of the cookie. It works similar to a timing attack and works like that. The attacker just triggers HTTP requests and adds some random string. Like now this would be a random string. I'll just set it to Alice to demonstrate it. So in this case, Alice and Bob would not match each other, so Bob and Alice are not that well compressed. However, if that string is Bob and down here is Bob too, then those two match and they get better compression. If this would just be Bo, then it would get better compression than Alice, but not as good compression as Bob. So you can try and you see that when the compression gets better, you're on the right path, and then you modify the string a little more, and if the compression gets better, then go further and further and further until you have the cookie. And now with this attack, you're somewhere down with running that in probably like half a minute instead of half an hour. And that makes me really sad, because I also don't really know what to do against it. Well, I do. So for one, you can update your browser, because the browser is in charge of generating that compression dictionary. So what the browser does, what modern browsers do, is just not take the cookie into account. You can turn off SSL compression, which is actually a really huge impact, and no one actually does that. Or what you can also do is you can append a random number of bytes to the response, because the way the attacker measures the quality of the compression is by checking the size of the response. Well, the problem is that this depends on the MIME type. So with HTML, you would need to do that in a comment. With image formats, I don't even know. I think there's like JPEG has some format to append random bytes to it, whatever. Yay, saved. But in June, there came a variation of this attack called breach. Yeah, I'm not even going to read it. It's like crime, but it's an attack against a response. Crime is an attack against a request. You figure out how the request is compressed, but crime is how the response is compressed. So you actually attack the CSRF token, not the cookie. Because once you have the CSRF token, you do not need the cookie, because you actually can do a CSRF attack from your awesome website again. And all you need to do is find an endpoint where whatever you attach to the query is also injected into the response. A typical case for that is a search page where you have the value back here, and then the page will just say no result for XXX. And then you just modify it till to get closer to the CSRF token. Then the CSRF token will be somewhere in a form in the body, so that part will compress better, and then you have the CSRF token in the end and can do a CSRF attack against. And this is actually, a lot of websites are vulnerable to this attack right now. It's not easy to do because you need to get the encrypted stream, and you at the same time need to roll a CSRF attack, but it's also not impossible, especially if you're, say, on an open Wi-Fi, etc. So what you can do is you can mask the CSRF tokens differently in every response. There's a pull request open for Rails, and it's probably going to be rejected. Oh well, don't use CSRF tokens. Do you all think about this when you write your applications? And I think the next attack vector is just around the corner. Alternatives, you can use the IP address, you can have the session ID in the URL. Don't. You can have a custom authorization header. That's what we actually do at Travis CI. The problem is all content, all sensitive content has to be loaded over JavaScript in that case. And then you can store that token in local storage and problem is solved. But that needs JavaScript, works well with PageX. I actually think we need new browser concepts that say, like, this comes from this workflow. But that's not there yet. So thank you. And I think I used up the time precisely, so I'm not sure if we have time for questions. You can also feel free to tweet at me or email me. Check out my blog where I basically never write anything. So thank you. Okay.
Are there any questions?
The last attack you said about the tunes, you didn't say if it's
I only really know what's going on in Rubyland. There is a plugin for Rails that fixes it at some cost. It's gonna be fixed in future Sinatra versions, but it's also not easy to fix. So that's not. It's also I don't really see how browsers can fix this, because that's something you need to fix on the server side. Because again, it's an attack against how the server compresses it and not against how the browser compresses it. Any more questions? Otherwise, just catch me later. I don't know. What do you say?
What are your alternatives to cookies?
So what we do is we have an authorization header that we set in JavaScript, which basically is kind of like cookies. So it's like we do like OAuth style where then have the token. But the difference is that only requests that are triggered from our JavaScript include this token, and requests triggered from, say, awesomewebsite.com, they don't know the token, they don't include it, so the requests they trigger are not authenticated. And that's the basic issue with cookies, is that whatever request goes to your domain from that browser will be authenticated, no matter what, no matter where it's coming from.
Basically, you say security by obscurity. Nobody else uses your method.
Nobody what?
Nobody else uses your method of the same authorization header, so it would be harder to break it.
Yes, because people don't know the value of there's no way to know the value of the authentication header, and or you could again do a cross-site scripting attack, whatever, but people generally don't know the value and they cannot trigger requests that include the value. Thanks.